Now let's discuss how you connect devices up to the computer. So there are two main ways to connect devices, and that's using buses or serial links. So buses are parallel, that is, they have many bits at once. So you have 32 wires, for example, and you can send 32 bits together in one clock signal. Serial links, on the other hand, send one bit at a time. They're serial. So if I want to send 32 bits, I need 32 clock cycles to send 32 bits. Buses used to be everywhere. In fact, until about 10 years ago, everything was designed with buses. Links used to only be used where distances were long. So networks used serial links because they were long distances. But what we're seeing today is that while buses are still used inside chips, serial links are now used for almost everything else. And we're going to discuss why it is that serial links are better than buses today and how this is changing in the future. So first of all, what is a bus and how are they used? So if we have a CPU and we have memory and we want to talk to each other, what we're going to do is we're going to have a memory bus. And so this is a bus that sends addresses and data back and forth between the CPU and the main memory. So we connect the CPU and the main memory to it. Now if we also have some I/O controller, here we're talking to some hard disks or something talking to a network, we also want to be able to talk to that from the CPU. So for that we're going to have a special I/O bus that these use to connect, and then we need some sort of an adapter or a bridge that communicates between the CPU bus and the I/O bus. So what are buses? Well, they're a shared communications medium. So as we see here on the CPU memory bus, we have three devices that are all on the bus. So all the wires for the address and the data and control are wired up to the CPU, the bus adapter, and the main memory. When we talk about controlling the bus, we can have one master, that is one device that controls who has access to the bus. For example, maybe the CPU controls who has access to the bus. Or you can arbitrate among multiple devices. So the CPU can ask, does anybody else want the bus? And if they say no, it gets it. And then maybe the bus adapter can say it wants the bus if it has data from the I/O. Now how does a bus generally work? Well, whoever's the master puts an address and a command on the bus. So the CPU says, I want to write to address 128. The slave, that is the device that's going to respond to this, receives the address and the command and prepares to get the data if it's doing a write, or send data if it's doing a read. So here the main memory knows that that's its address, or that that address corresponds to it, so it prepares to receive data. The next cycles, the master is going to put data onto the bus, and the slave will store it. So here the CPU can put some data on the bus, and the main memory knows that it's expected to write the data, so it gets the data and knows which address to write it to. If we're doing a read, it would be the other way around, where the CPU would wait for data from the main memory. So what is a bus physically? Well, it's just a lot of wires. So here's our processor and our memory, and we're going to have wires for the address, and wires for the data, and wires for the control. So if we have wires for the address, maybe we have 8 of those, 8 wires for the data, and a bunch of wires for control. Here we have a wire for reading, a wire for writing, and a wire for the clock. When we want to send data, we're going to need to set up the data on the wires and send the control and the clock signal. So to send this data, we just go and set the wires to do what we want, and the device gets the data. Now you'll notice here the device is also getting the clock signal, so it knows to write the data to the address on the clock. So the example we have here, we have separate data and address buses. In the previous example, we had one bus that we used some of the time for data and some of the time for address. And which way you decide to design something depends on whether you want to have more wires or fewer wires. So what's the big problem with buses? Well, what happens if signals are late? So I want to go ahead and send this data, but this time some of my wires take longer than others. So I go ahead and start sending the data, but it doesn't all get there at the same time. So here's the data I wanted to get, but when the clock edge rose, so when the clock became 1, here was the data I actually had. So I'm going to go ahead and write the data to the address when the clock rose, but I didn't get all the right data. So now because some of those wires were slow, I've corrupted my data. The only way to handle this is to slow down my clock speed so all the data gets there in time. So what's the problem with buses? Well, it's basically that the wires are ugly. And they're more so as things get smaller. So as we have smaller and smaller wires and want to run faster and faster, wires get harder and harder to manage. And the reason for this is that wires have capacitance, inductance, and resistance. They're complex circuits. And this makes them slow. And particularly with buses, if we have multiple things on the bus, each one of those things on the bus adds more capacitance, more inductance, and more resistance, and slows down the wires. Wires also interfere with their neighbors. If I have a wire next to me that has a 1 on it and I have a 0 on it, that 1 is going to try and pull on my 0 when it changes. So you get noise from your neighbors. So the real problem with buses is it's very hard to keep wires synchronized to the same clock. So if I want to have 32 wires to have a 32-bit bus, I need to make sure they're all synchronized to the same clock. And this is difficult. Let's take a look at an example of that. So here's a circuit board from a graphics processor, and you can see all the traces on it. These are wires coming out from the processor. Now if you look at the side here, you see an awful lot of very squiggly wires. And the question is, why did they make these wires be so squiggly? They could have just run them directly. And the reason is they're trying to make all the wires the same length. So by adding these extra squiggles, they're trying to equalize the wires so that the data on the wires all get to the destination at the same time. Now it's not just the lengths of the wires that's a problem. If you look at all these holes, these are vias. Each time a wire goes through a circuit board, it adds capacitance and inductance to the wire and slows down the wire. So you need to balance the length, you need to balance the number of vias you have, and a whole bunch of other things to make sure you can run your wires quickly.